Okay, good morning. This is the I think it's the fifth talk in this series, and this is going to be the last one. And hopefully, this should complete the picture. And after this, you should have a good understanding of all of Ballerina. So this section is this part is a bit of a mixed bag. It's really just filling in the gaps and showing how everything kind of fits together. So in no particular order. So functions can have default values. You can do equals and then you have an expression. And that expression can use the values of preceding parameters. And the way that works is that when you call a function, there's a type, you always have a type descriptor for that function. And that type descriptor contains closures for every defaultable parameter, which has the values of previous parameters as parameters for those closures. And the caller, it's up to the caller to use that type descriptor to fill in missing values. But when you're actually using functions as first-class values and passing it around, it's not part of the function type in that sense. There's quite a subtle distinction between type and type descriptor. Type is just like a set of values. Type descriptor is a way of describing a set of values, and it also has a few other bits of information like defaults. You can also provide function arguments by name. So if you have defaults, it's quite useful to be able to, you sometimes only want to specify particular arguments. And you can do that by using the names of the arguments. And it works in, so I think the important thing to realize is that names of arguments are significant. So if you need to think about what names you're using when you're designing API. You need to think about those names and you have to commit to them because it's part of the public interface of your module. And one of the reasons we did this is so we have a uniform model for regular object methods and both remote methods and resource methods of service objects and client objects, because often for those kinds of methods, names are significant. Like you're calling GraphQL, for example, names are significant, or all functions are, the names are significant, or HTTP query parameters, names again are significant. So, so often when you're combining, you often want to create a record using fields of other records. So let's give a little example. Suppose you have a date record, which has a year, month, day field, year, month, day fields. You have a time of day record, which has year, minute, seconds fields. You can create a time record, which has all the fields of date and all the fields of time using this star syntax. Star means basically copying the fields of that record into this one. And that copies in defaults as well. Actually, I haven't said that, have I? Okay, we haven't got defaults. So we will see later that when you do that, these can have defaults, then be copied in. So there's one interesting problem when you're designing APIs in Ballerina is that really, now we have named arguments and we have records. There are really two different ways you could do an API. You can have separate arguments for each, and it's often common when you're designing API, you've got a bunch of options, and there are quite a number of them, and there are two different ways you could do it. So you could have named arguments, and each one is a separate, each of these options is a separate named argument. The caller uses option name equals value when it wants to supply a value. Another way you can do it is you can have a record that defines all these options, and then you use a single argument that has a record constructor in it with curly braces. And there's no real right answer for which is the right one to use. And that's confusing for the user because with named arguments, you use one syntax, and with when you have a parameter that's a record, they use a different syntax. So we try to give the user a uniform experience by having this concept here of I need to annotate so you can see me. Okay, so this thing here, you see the star here. What that is doing is it is conceptually copying it from the caller's point of view. It is copying in all the fields of this and making them available as named arguments. So when you do this, you've kind of got the best of both worlds. You can have the same, you've got the same experience as if you have named arguments. You just supply it just as if verbose are being named arguments. But the user here can then define it as a record. So there's really no need in this sort of situation to have a regular, you shouldn't ever really, in this sort of situation, design the API just to have a regular record as a parameter when it's applying options like this. Instead, you should do it as an included record parameter, and then the user doesn't have to worry about the fact that you're using a record here. The user just gets a uniform experience, which is that these things are named arguments. Why is that not working? Okay, so as I said a bit earlier, prematurely, record fields can also have defaults, and it looks like what you'd expect. And that is part of the type descriptor. So here we've got an X record and we have a strut field which has a default value. So here that we know we're constructing an X. So this record constructor here there's no strut field, so it will use the default that's defined in X, and the value you get here will have an empty strut field. And this also works with data binding. So when you're using clone with type, that will get the defaults. And that default value is part of the type descriptor, and it's basically it's a closure. So that could use variables defined in a module. And when you do star T, that will copy the default values. And what it actually copies is not the literal expressions, it copies the closures. So if this is in one module and this is in another module, this is an expression, say, refers to a variable in this module. Everything will work properly. Things will refer to the right variable as you would expect. Okay, so we've seen object constructors, and we've seen classes as the way to create objects. We also have object types. So an object type is just a type for an object. A class gives you two things. A class gives you a type for an object plus an implementation of that type, which you get when you use new. But you can just have the type by itself. And that's a bit like an interface it's kind of like an interface in Java. So it's the type without any implementation. And it just looks like a pattern for the object. So this is an object type, and an object value belongs to the type if it has a function called hash that returns an int. And so here's a little example. We're going to create an object. And so typing of objects is structural, works just like everything else in Ballerina. Here we have a little function, and I'm going to create an object, and it has a hash function called hash, returns an int. Not a very interesting function, and I've assigned this to an object, and I am returning this for a function that returns a hashable, and this is okay because what's hashable? It just needs a function called hash, returns an int. Yes, this function has a function called hash that returns an int, so it belongs to that type. So although it's like interface, this is not nominal typing, this is structural typing, just like everything else in Ballerina. So we saw including record types with star T. You can also include object types with star T. And you can use this in two cases. One is when you can have a type include another type, and that is like having one interface that extends another interface. And you can also have a class that includes a type, and that's like a class that implements an interface. So in this case, here we have a clonable. I've made up a clonable type, and so in here we've done clonable, so it belongs to clonable, and it also has another function. So this just copies in that to there. So note the Ballerina doesn't have implementation inheritance. You don't copy, you never copy implementation, you just copy types. So what we're doing here is we're copying in the types, and then we provide implementations. And this checks for us that this will get us a compile time if we hadn't defined a clone, or we defined clone in a way that wasn't a subtype of clone here, that would get us a compile time error. So here, notice that we have made the return type be a subtype of the return type here, and that's okay. You can override anything, provided you override it with a subtype. So the net result is when you do star shape, you're guaranteed that circle is a shape. Okay, so we can also regular, as I said just now, regular object types are structurally typed like everything else. But we do have a way to do, sometimes it's useful to have something that works more like Java that's nominally typed, where the name is significant. And we do this with distinct object types. You remember we had distinct types with errors. So distinct is basically a keyword that goes before a type and says, make this thing be a distinct type. So that means make this thing be something that has its own little tag, and it's not just this. It has a distinct ID that is different from any other object type. So here we are making a object type, and we're saying we don't just want to identify it by its structure. We want to make it distinct from everything else. And now we have an employee type, and we're including person. And what this will mean is that the employee belongs to this distinct object type, and it also belongs to this employee object type. So it belongs to, so we have multiple inheritance here, multiple interface inheritance. So employee, well, this one doesn't demonstrate multiple inheritance, but so conceptually, an object has multiple tags. So when I create, a person object, so when I create an employee object, it will both have the tag for person, and it will have the tag for employee. And so if you ask, is employee, that will be true. If you ask, is person, that will also be true. And here we've got done the same thing. So even though these three are all the same structural type, they just have one public field. So from a structural point of view, they're exactly the same. And so this is just a type. This is a class, which means it has an implementation and a type, but the type defined by the class are the same in all three cases. But you can still distinguish them. You can, if you've got an object, you can say, is it an employee person? Is it an employee? Is it a manager? And depending on how it's created, you'll get a different answer. So this gives you, within the overall structural typing framework of Ballerina, it allows you to do nominal typing if you want. Why would you want to do that? Well, one reason is you're trying to interop with things that use nominal typing. So if you're trying to do interop with Java and you try to do structural typing, it just ain't going to work. You'd have to fake it. So this allows you to have, if you're doing Java interop, you want to make the class corresponding to each Java class be a distinct class so that you correctly capture Java semantics. But most of the world, object orientation in most of the world is in fact nominal, not structural. So when you're interacting with the outside world, typically you're going to want to use, you will often be wanting to use nominal typing. And GraphQL is another important example that is nominally typed. But it can also be useful when the name of the fields doesn't give you quite enough, isn't quite enough to distinguish. You want something a little bit stronger than that. But this is very much not data. when you're doing objects and you want to, you sometimes just thinking structurally doesn't really do what you want for objects, and you want to think more normally. But that's really it. So there's no hard and fast rule about when to use distinct, but don't overdo it, would be my advice. If there's some real reason why you need to use distinct, use it, but don't just make everything distinct because it feels warm and cozy and like Java. Objects can be read-only. We saw that any data can be read-only, but objects can also be read-only. If you want to get a read-only type, you can just use read-only together. You just read-only and with the object type, just as usual. If you now want to have a class that belongs to a read-only type, there's no way to stick in the ampersand here. So instead, you've got to declare the class as being read-only. So that will then, this read-only class will actually be the type defined by that class. Not only will the specific values that you knew with this class be read-only, but also the type. Every class defines both a type and implementation. The type defined by this class will also be a read-only type. Okay, so errors. So one thing I haven't explained yet about errors is that we saw that errors have a distinct type, and we saw they have a message. They can actually have an arbitrary payload, if you like, which is a record, which can be whatever record you like. It has to be something that can be cloned and made read-only, because we want errors to be immutable, so you can pass them around between threads. But apart from that, it can be anything you like, and you can constrain. You can write an error type. So if you want to put arbitrary details in, you just use the named argument syntax. So here's a bit of extra data you want to put in, and you can also constrain. You can describe the error. You can get some checking. You can describe the error detail as a type parameter error. So this type error HTTP detail means it's an error whose detail record belongs to the HTTP detail type. So if you put something here, well, you use an open record here, so it's not going to check so much. But if you'd use a closed record here and said, this is all you have, if you put something else there, it would say, no, you can't do that. And then when you want to get the detail out of the record, you use a langlib function in error, and you can get the detail out. So that all type checks neatly. We also have, separate from the error detail, errors can also have a cause, which is, like in Java, it's what caused the error. And you give that as the second positional argument. It's an optional positional argument to the error constructor. So here we are basically wrapping. We're wrapping, so int from string, if that fails, the result of int from string is either an error or it's int. If it's an error, then we wrap it in another error and have this as the cause and return that. Otherwise, we return the int. So you can, if you want, record that you can wrap errors in that way. So you might be asking, well, you should be asking, in fact, if you've been paying attention, well, I can write a distinct error type and I can constrain an error like this. But what if I want to say it's both a distinct error type and it also has this error detail? How do I do that? Because you remember with objects, we were doing star T to get that. But errors don't have a body. There's no place to put the star T. So how does that work? Well, the answer is you can use type intersection again. So if I've got a distinct error type IO error, and I've got a detail record, so maybe I want to give the name of a file name, I can have an error. I can constrain an error both by saying it belongs to this distinct error type and has this error detail record by using the intersection operator again, just like we saw with read-only. And in fact, type intersection is a fairly general feature that you can use with a bunch of things. In particular, you can use it with object to do some things a little bit more neatly than you can do with star T. So if I want to have an object, I have an object type foo and an object type bar, and I want to combine those, I can do foo and bar. And that's exactly, that will have the same result as doing star foo star bar. It's not quite as flexible as the star T feature, but it is, it's when it does what you want, it's a bit neater. So Ballerina's general philosophy is we want to try and do things in a way that's familiar to people who know C or a C family language. And so we have a distinction between expressions and statements, just like C does. But it's actually a more generally a better way to do languages is generally to have a more expression-oriented language where everything's an expression. We haven't done that because it's just not, it's less familiar. But we make a nod in this direction by trying to allow you to do make it possible to do more things with expressions and encourage the use of a more expression-oriented style. And there are a couple of little features that support that. We've already seen query expressions. Again, that's a very powerful thing, allows you to do a lot with expressions. Constructors, so when you're constructing a map with a constructor expression or with a constructing an array with an array constructor, that's also an expression. And also nil, our concept of nil is another little example. Functions that return nil they return a value, so they're expressions and can be used in expressions. So we've got a couple of other little features that help with encouraging you and making it possible to do more of the expressions. If the body of your function is just return an expression, instead of having to put curly braces, return the expression end curly brace, you can just use this same syntax that you saw with lambdas, with anonymous functions. You can do that here. And that works in objects too. So we have a method here, but it's quite convenient when you're just returning a private. When you're doing a getter, it's quite convenient. And we also we saw let. You remember we saw let in query, and we have let available generally as an expression. So you can do let. You put an in when you're using an expression. You have in. So this is an expression that binds x2 to. So we're computing x squared plus x squared plus x squared. That's not quite right, is it? Anyway, I think that's supposed to be xy. I think I've forgotten my maths. Anyway, that's not a very good example. But anyway, so the point is you've got a let here, and you can do you can have a temporary variable, and that allows you to do more with expressions. Another little thing that helps you do more with expressions. Actually, this is a JavaScript. This comes from JavaScript. If you want to have in a map, sometimes your key is actually computed rather than being known at compile time. And if you have a computed key, you can instead of having to use an assignment to add to it, to create an empty map and then use statements to add to it, you can do it in a more expression-oriented way by putting the expression in square brackets here. And one actually very useful case of this is if you have some complex key name. This is not a very complex key name. Suppose you have a key name that's a URL or something, or some big complex string that doesn't look like an identifier, and you want to put that in a context constant somewhere, you can do that and then refer to the constant. So tuples. So we've seen arrays. So we've seen records and maps as being two ways of describing a list. And sorry, start again. So we've seen records and maps as two ways of describing a mapping. There are also two ways of describing lists. So what we've seen so far is an array. With an array type, you are giving one type, which applies to every member of the list. With a tuple type, you are specifying individually the types for each member. So this is actually, if we have this type here, we can have a fixed, that's the same as a fixed length array. So that's a float of length 2 is exactly the same. We can write it in this syntax too. So that means it's a it's a two tuple with first member being a float and the second member being a float. But you're not restricted to have, obviously you're not restricted to these things being the same type. I suppose I want to have an ID type that has a string and an int and an int. Then I can do that too. And sometimes you want to, when you've got a fixed length array, sometimes you want to infer the length of the array from the initializer. And the star here says to, it's a fixed length, but get me the length from the, infer the length from the initializer. And once you've got a tuple, you need to be able to get access to the members of the tuple. You can use a normal array access, but it's actually a little bit cleaner to use destructuring. So suppose I'm representing a time type by an int, so it's the days, and decimal is the seconds from midnight. And I want to just convert that into seconds, because I don't care about leap seconds. So we can use a little binding pattern here. So I can say, take this and destructure it into two variables. So this will make the day be an int and the seconds be a decimal. And this declares two variables and initializes them from this tuple. And then I can convert the day's an int, so I need to convert it to a decimal, multiply it by the number of seconds in a day, and the seconds to it, and I'm done. So if you see a tuple, it's clean. The cleanest way to deal with tuples is via destructuring rather than via. I mean, you can use index access, but it's kind of not really idiomatic. This is the idiomatic way to do it. And you can also use binding patterns in an assignment. So this is a simple example here. I've got two variables. I've got a type that's a pair of ints. I can use an assignment here to assign this, and this destructures it into and assigns the first member of the tuple to X and the second member of the tuple to Y. And if you go the next degree, this is quite a fun thing you can do, which allows you to swap two variables without using a temporary variable. So what this is doing is constructing a tuple, and then conceptually what it's doing is constructing a tuple and then destructuring it and assigning to that. But of course, a compiler can, in theory, I haven't actually checked what our compiler does, but a compiler can, in theory, compile that down to something that does the most, swaps things in the most efficient way. So we also have, so you'll remember that with record types and map types, that actually any map type can be described as a record type by using t dot dot. And actually, we have the same thing in tuples. So this is a type which describes lists whose first member is an int, and then other members are strings, any number of them. And so actually T, like this, an array type T is the same as a tuple type, which just has T dot dot dot, T dot dot dot. So we have the same thing going on in tuples as is going on in records. So we actually have quite a nice symmetry between arrays and maps. So we got basically two kinds of values. We got lists and mappings. Lists are indexed by ints, mappings indexed by strings. In JSON, lists are represented by arrays, mappings are represented by JSON objects. You construct lists using square brackets, you construct mappings using curly brackets. And we have two different types you can use to describe each of them. Array type, when you have a type where you want to use the same type for every member, you write it T like this, an array type. And then we have a map type, which describes mappings where members are the same. And when you want to have a separate type per index, you can do it with a tuple. That's the type for index 0, the type for index 1. Here's the type for key X, here's the type for key Y. And we also have an open type using dot dot dot. So I think that's quite a elegant, for people who care about that sort of thing, That's quite an elegant symmetry there. So we've seen a rest type in tuples and records. Parameters can also have a rest type. So you can say string ... s, which means you can have any number of string. The caller can supply any number of string parameters. And when it does so, all those string parameters gets bound up into a list. So if I call foo like this with 3 string arguments, then s will be get the value that's a list of 3 values. And this same thing then also works on services for path parameters, on resource methods for path parameters. If you want to have a syntax where you can say, suppose you want to be able to say file /x / y / z, any number of things, and you're going to somehow, maybe it's an API that gives you access to a file or something, then you can do that just like this. You just use the same string ... syntax in your path parameter, and then you can go, you'll get, that will be path will then be bound to an array of strings. If you put it with /x file /x / y / z, you'll get this array of strings. So the other kind of side of the coin of, we've seen x ... now we're saying ... x. And this is what, this is JavaScript has this too, and it's called they call it a spread operator. And the basic idea is when you say ... x, x can be a list or x can be a mapping, and it's equivalent to specifying each member of x separated by commas. If it's a list, then you're specifying them positionally. If it's a mapping, then you're specifying them by name. So here's a little example where we're specifying them by name. So we've got a date type, which is a closed record with 3 fields, a time of day, which is a closed record, 3 days with 3 fields. And then we're going to make another record with both of those. And now the task is we want to create, we've got a date, we've got a time of day, and we want to construct one of these. So we can just do ... d, and what that means will be, it will take each of these fields and specify them here. And ... t means it will take each of these fields and specify them here. So this is the same as a record constructor, which specified 6 fields, year, month, day, hour, minute, second, and that will construct us a date time. And this spread operator works in a bunch of different contexts. You can use it with a function call, in which case x can be a list and you'll get the arguments positionally, or it can be a mapping and you'll get the arguments by name. We can use it in a list constructor, in which case this x must be a list. We can use it in a record constructor, in which case it must be a mapping. Or you can use it in an error constructor to stretch an error value, in which case x must be a mapping. So it works in a whole bunch of different situations in a uniform way. And the basic rule is that it's got to be type safe. This shouldn't lead to runtime errors. The type of x must ensure that the type, when you do ... x, you've got to ensure that the types will lead to the resulting expression being valid. So for example, this wouldn't, if this was an open record, I mean, here's an interesting example of where you'll get an error is, suppose these were not closed records, but open records. This would not work then because this could have an extra field called foo, and this also could have an extra field called foo. So if you did that, you specify, there's a possibility of specifying foo twice. So that would not type check. And we can also use spread in binding patterns. This spread operator also works in binding patterns. So we can use it, suppose we had a tuple type, which uses a rest type here, and we want to destructure that using a binding pattern. We can use a spread operator to do that. and that will destructure this tuple, and path will be bound to an array of strings. So we could then destructure it and then iterate over each of those strings. And this is actually useful with the spread in binding patterns is particularly useful with open records. We'll see an example here. So here we're using a binding pattern in a match statement. So actually, when you have a match statement, when you have var to say there's a variable bit, what goes off of var isn't just a variable, it can actually be a binding pattern. And that binding pattern can use the spread. We can use a spread operator here, and we can use spread to capture the rest of the binding pattern. So this here will so here this is an open record. So it's got X field and Y field, and it's got some other fields. We don't know what they are. It's open. So what this will do, this will bind X. So this pair, X, the X variable here, will be bound to the value of the X field of pair. So we're matching it against the pair. So the X field, the variable X will be bound to the X field of pair. The variable Y will be bound to the Y field of pair, and rest will be bound to a map of everything else in pair. So you've actually got a way to conveniently process all the extra stuff. You know, not only do we have open records, but we've actually got a way you can actually do stuff with them. Now, here's a little puzzle for you to think about. What is the type of rest? Now, you could say that the type of rest, it's a map of any data.
I thought it's going to be nil. I thought it's going to be nil.
Why would you think? Well, it's certainly not going to be nil. It would be a map of any data is a good approximation, because this is an open record. So you can have you can have any other fields you want here. So in general, you can have a map of any data, but that doesn't quite capture it, because it doesn't capture the fact that you can't have an X and you can't have a Y. So we know about rest. Not only do we know that the values are any data, we do know something about the keys of the map, and that is that they ain't X and they ain't Y. So how on earth do you write a type for that? Well, this is slightly mind expanding, but that we have a never type, and a never type is a type to which no value belongs, which may not sound like a very useful type, but it does have quite a few, surprisingly large number of use cases, in fact. So one use case is for a function that never returns normally. So the return type of function gives the type of the function if it returns normally, that is, it doesn't panic. There are two ways a function can return. It can panic or it can return normally. So never actually is actually a perfectly useful and reasonable return type for a function. It means it never returns. Or to put it more, to give the full story, it can only ever return via a panic. Another use case, in fact, TypeScript TypeScript actually has a never type. There are quite a few languages that have this type. TypeScript uses the name never we got from TypeScript. So another example is stream int never would be an infinite stream of ints. It never returns. It can never return normally. XML never. What do you think XML never means? Well, the argument for XML is all the possible things that can occur in the sequence. If nothing can occur in the sequence, that means it's an empty sequence. So this is actually a way to write the type for the empty XML sequence. And another interesting case is, so how do we write the type for, so we had now an example for a pair with X and Y. It's got some extra data here. So we've got X1, Y2, and then we've got another field called color. So we use a binding pattern here to define a variable rest, and that is going to be bound to the fields other than X, Y. So in that case, it will get a map with key color and value blue. And what is the type of rest? Well, we can actually write it like this. So it's an optional field. So an optional field means if the field occurs, it must have this type, but it can't occur with this type. So the net result is you can't have this field. But it does affect when you say this is implicitly open. And what that means, it can have other fields, it means fields other than those named. So when you say this means implicitly any data ... and that means any fields other than the ones named in here. So you can't have X and you can't have Y because they're named in here. So this actually allows you only anything other than X and Y. So that's actually quite useful because now I can use it with a spread operator and other values of X and Y to create a new pair. But so this is a fun trick. You don't have to, if you don't understand, don't worry, but it's quite, I think it's quite fun. Part 3 is where we have the fun, cool stuff. Well, part 2 has fun, cool stuff. So sometimes you want to interface to external code. We do this a lot at the moment in Java, but it works equally for C. And so you can say that the body, you can use equals external. Instead of providing body, you say equals external, and then it's up to the implementation to figure out how to get that implementation. We don't go into that. And we also have the other part of our story for interfacing with external code is that we have a separate basic type called handle, which you can't do anything with basically other than pass it to an external function. So if you've got an implementation, as we do, based on the JVM, you might have a handle corresponding to a Java object. And all you can do is pass that to an external function. If you've got a C implementation, a native code implementation, it would probably be a pointer of some kind. But it's basically an opaque handle that you can pass to external functions. And there's no typing of these things. So you can ensure that programmers use this safely by making the handle be a private member of a class, of a Ballerina class, and then your Ballerina class can enforce type checking of that. Another feature that is particularly useful for interfacing with external code is built-in, this concept of built-in integer subtypes. So we only have one int type, and that int type is 64-bit signed type. But actually, the outside world code that we need to work with uses a bunch of different integer types, and we have to work with that code. And so you can do this by using, so in the Lang library int module defines a bunch of built-in types that you can reference like this. We have signed and unsigned for 8, 16, 32 bits. This one here, int unsigned 8, is the same as byte. And the important point to understand here is that these are not separate basic types. Operations on these types works exactly the same as int. So there's really nothing to understand. If you know how int works, you know how all these things work. There's not something separate to learn. You can think of them as just big unions. So int unsigned 32 is just a union of 2 to the 32 things, which would be a bit inconvenient to write. Just as a byte is really a union of 256 things. So these are really just big unions of ints. It's a fairly lightweight feature. And this is useful for when, if you're going to be calling, suppose you've got as C does, you've got an sran function which sets a random seed, and that expects an unsigned 32-bit value. And we want to be able to describe that. If we just say int there, well, that just doesn't describe what's going on. So if we described sran like that, okay, so we can call it 72. 72 is an int, but it's also an int unsigned 32. All int unsigned 32 is its value of the int is between 0 and 2 to the 32. 72 is, so that's okay. We have a little bit of special typing. We know, just as a matter of mathematics that, or maybe I should say logic, I don't know. If you take any integer n and you AND it with something that's an unsigned 32 bits, you will get something that is 32 bits, because we know that the upper bits are 0. So we just know as a matter of logic that this will in fact give you something that's unsigned 32, so that's okay. You can also cast it. In this case, the behavior will be different. If you have an n here that is not in range, then when you do that cast, that will panic. So it forces you to, think about how is it that you're gonna, this code actually accepts unsigned 32-bit ints, R ints are 64 bits. You've got to think about and be explicit about how you want to interoperate. And we actually have this built-in subtype concept. There's another case where we have it, which is for strings. You'll remember that we don't have a separate character type. Rather, we represent characters by strings of length 1. So the char type is actually a built-in subtype of string, and a string belongs to that built-in subtype if it has length 1. This is not a big feature, but there's one important operation that you can do on length 1 strings that you can't do on other things, which is convert them to a copoint. A string of length 1 is something that means something that has a single copoint, so we can apply the toCopoint int operation on our char and get a copoint back. And if x here wasn't, we know that x is our length 1, so we can assign it to this, and then we can do copoint on it. And string char is a little bit like the built-in subtype XML element or XML text. It's a similar concept. Okay. So I think we've seen all the basic types so far, apart from type desc type. I mentioned it briefly earlier when I was talking about the data binding feature. So it's a built-in type, and it represents a type descriptor. It's immutable, and it has a type parameter that says what is the type of thing that belongs to this type descriptor. So if I got a type descriptor type desc t, a type desc value belongs to that if it describes a type that is a subtype of t. So here I've got a type R, that's a record. Now I can get a type desc for R just by referring to R. If I use an R in an expression here, that gives me a type desc value. And I can assign it to T. So T is a type desc, and it has the constraint that the type it refers to must be a record type. And that is true for R. R is a record. So R is a record, so the type desc for R belongs to type desc angle brackets record. So that assignment's okay. And we also have a type of operator, so I can get the type of. So suppose I've got an R, I construct an R using this. I assign it to any, and I ask for the type of this, which is a type any. So what type of is doing is ask me for the dynamic type, the runtime type. And for a record, that is the type you use to construct it. So if I do type of V, what I will get back is R. So this function here will return true because I got the type of R in a type desc and put it in T. And I also got this thing here, this record, its type is R, and I can get that with type of. So they're the same thing, and I can use equals to test them whether they're the same. Now I think I mentioned the ensure type function earlier. That's a langlib function, and its argument has an argument that's a type desc. And this is like a cast, but with a cast, if you can't do the cast, you get a panic, and that's often not what you want when you're dealing with user input. You may not want that. You actually may want to, or you're parsing something from JSON. You typically don't want to give a panic if you've got bad data. You want to give an error. And so with ensure type, basically this is doing the same as casting B to float, but it will give an error if it's not a float rather than panicking. Now, if you look at this, so this is just a call to a langlib function that's defined in the lang.value module. Now, if you're looking at this, you should be wondering, well, how does that work? How is it that there's no cast here? Because V's any data, I put float here. How is that I don't need a cast to float? How is it I don't need a cast to float or error here? And this, the reason you don't is because we have a funky feature called dependent types. And the concept of dependent types is that the type of the result of a function depends on the value of a parameter. So usually you specify the type of the return value and it's just independent. It returns an int or returns a string. The value of the return value may be dependent on the arguments, but the return type doesn't usually depend on the parameters. But we have a special feature whereby the return value, sorry, the return type can depend on the value when the parameter is a type descriptor. So if we look back to, so just here's an example from ensure type. So we're calling this with method syntax. So in this case, v here is the first argument and float is the second argument. So we've got a float value here, and we've got a type desc, which will be the float type here. And what this says is that this either returns an error or it returns a value whose type is the same as the type given in this parameter. So in this case, that means that the compiler knows what float is here. So it knows that this returns float or error. Now, there's a big limitation at the moment in that you can't actually implement these. We don't currently allow you to implement these functions in Ballerina with this kind of typing. You have to implement that externally, but I think we'll be able to remove that limitation in a little bit. So what this means is that, oh, I put that wrong. That should be j.ensure type, not, sorry, let me just fix that. That should be, actually, let me not try and fix it. That should be j.ensure type rather than. So here, basically, you can leave out the float parameter, and that comes from these little angle brackets here. And what this means is that this parameter can be defaulted from the contextually expected type. So here we could actually leave out float, and the reason we can leave out float is that we've said here that this returns a float or error. So we actually know what we want, and we can default it. The caller can default it from that context. And we're doing a little bit of type unification here because we've got this possibility of error here. So that should be j.ensure type, and then the j parameter is the first parameter here, and then the second parameter here is inferred from this. And okay, so that's one case you use, one big important case of using type desc values is for these type manipulation functions. So clone with type, from JSON with type. There are a whole bunch of with type functions that are kind of used that are very important for data binding, and they all use type desc values. Another place where you use type desc values is to get access to annotations. So we saw how you can put annotations on things using the @ syntax, but it's also possible to define your own annotations. And the way you do that is with an annotation declaration. So what you do in an annotation declaration is you declare a tag. So here we're declaring a tag constrained int. And we're saying that the type associated with this tag is int constraints. So define this record type. This is the data that's going to be associated with a constrained int tag. So when, if I declare it in module M like this, then I can use it like this. So I've got the constrained int tag. This is an optional field. Here's another optional field. So I'm just using the min inclusive field. And this is the data that's associated with this field. So what this declaration says is, it's an annotation declaration. This is the tag that's been defined. This is the type it has. And this on thing says what it can be applied to. So this is typically the keyword of the kind of declaration that applies to. So here we're applying it to a type declaration. We're saying this can apply to a type declaration. So when we have that, we can then access this using this .at operator. So the way that works is we have positive in here. We get a type descriptor. So we define a type here. We reference it in expression to give us a type test value. We then use the .at operator, which is kind of like a field, like a member access operator. But what goes after .at is a annotation tag. So you've got this annotation tag here. We're accessing it here. And what we get is this record type. But of course, we have no guarantee that we applied this tag to this type. So that's a question mark. So it's that or nil. So if this tag had been applied to this type, we'll get back an int constraint record. If it hadn't been, we'll get back nil. And I think this is the final thing. So usually you don't want to track panics, but sometimes you do. And there's a specific trap. Panics and errors are not the same thing. And there is a way to trap panics if you need it. And it's called trap. And what trap does is it takes an expression. It evaluates the expression. If the expression panicked, it captures that panic and returns as an error. So if this is type, so this here is type int, and trap applied to that, the type of that will be int or error, because you don't know, there's nothing in static typing that tells you whether you're going to get an error or not. So this will give you type int or error. And so so remember that if integers overflow, that panics rather than just being ignored. So this is a way to do an add that will give you an error if it overflows. So we're just trapping that, telling you an error. And so the type here is int or error. And I think that is it. Yes, that's it. You have now seen pretty much all of, there's a lot of detail. So you can download the implementation. I'm sure you all know that. I wrote a couple of blogs on Ballerina, which explain a little bit more about the why. Obviously, they're the online docs in the on the ballerina.io site. And there's also the language specification that has all the nitty-gritty. It has all the nitty-gritty details about the language. It's basically a designed to be a record of the design. So the implementation team knows what to implement. And then we have so I maintain the spec in GitHub here. And if you have issues or questions if you've read the spec, you have issues or questions, please feel free to ask a question here on issues. If you want to get my attention, the way to do it is to create an issue. And I try to answer all issues. So if things are not clear, feel free to raise an issue here. Okay, thank you all very much for, it's been a long journey. Thank you very much for joining. And I'll stop there.